Okay, let's dive right into this. Welcome to our latest explainer, where we're going to deconstruct the fascinating and honestly surprisingly dangerous world of artisan carbonated beverages. You might think pouring a soda is just about mixing some sweet syrup with bubbly water. But today, we're unlocking the actual science behind your favorite fizzy drinks. We're talking everything from the precise thermodynamics of carbonation to the rigorous stovetop safety protocols you absolutely need to know to brew this stuff at home. So here is our roadmap for today's deep dive. We'll kick things off with Section 1, the physics of fizz, and Section 2, water chemistry and prep. Then we'll move into Section 3, formulating artisan flavors, followed by Section 4, pathways to carbonation. And finally, we'll wrap up with Section 5, surviving the bottle bomb. All right, let's start right at the very foundation with Section 1, the physics of fizz. Before we even think about flavor, we have to understand the physical chemistry of how gas actually dissolves into a liquid. And to do that, we have to talk about Henry's law. This is basically the golden rule of carbonation. It states that at a constant temperature, the amount of gas dissolved in a liquid is directly proportional to its partial pressure. But what's the practical takeaway for your kitchen? Well, it's simply this. Colder liquids hold significantly more carbon dioxide than warmer ones. And once that CO2 is dissolved in there, it doesn't just sit still. It actually reacts with the water to form carbonic acid, which drops the pH and gives you that crisp, sharp bite that makes soda so refreshing. So what does carbonation actually feel like? Our sources point to a very specific metric, 0.6 volumes. That is the exact physical threshold of dissolved CO2 where the human palate begins to detect carbonation. If your beverage drops even slightly below 0.6 volumes, your brain just perceives it as completely flat. And this perfectly illustrates how carbonation is definitely not a one-size-fits-all thing. The math directly dictates the mouthfeel. Just look at the stark differences here. A British cask ale sits really low, right around 1.5 to 2.2 volumes, which gives it this soft, almost creamy texture. Then you move up to a typical lager, hitting 2.4 to 2.6. By the time you're drinking a highly carbonated cola, you're at 3.5 to 4.0 volumes. That's where you get that highly active, aggressive prickle on the tongue. And traditional champagne, that tops the chart at 4.6 to 6.0 volumes for this intense, explosive effervescence. Moving right along to Section 2, water chemistry and prep. Water is the primary solvent in our soda, which means we seriously need to talk about the hidden dangers lurking in your municipal tap water. So, municipal water is treated with chemical disinfectants to keep it safe, primarily free chlorine and chloramines, which is great for public health, but absolute disasters for artisan beverages. These sanitizers easily destroy the delicate yeast needed for natural carbonation. Even worse, if you leave them untreated, they react with natural phenolic compounds in ingredients like vanilla and ginger to form trichlorophenols. And trust me, you don't want those. They're nasty compounds that will literally make your meticulously crafted soda taste like medicinal plastic or hospital gauze. Now, free chlorine is volatile, meaning it easily boils off. But chloramines, they are highly stable and stubbornly resist boiling. So, how do we get rid of chloramines? The answer is chemical reduction. The standard protocol requires adding a quarter teaspoon of potassium metabisulfite, which you'll often see sold as Campden tablets, per 5 gallons of water. You drop that in, wait 24 hours for the reaction to break the chlorine-nitrogen bond, and then you boil the water to release the trace amounts of sulfur dioxide gas that get produced. Only after you do that is your water a safe, blank canvas ready for flavor. And that brings us perfectly to Section 3, formulating artisan flavors. Acidity is a foundational killer of any soda. It balances the sugar, acts as a protective barrier against microbiological contamination, and stimulates salivation so you want to keep drinking. Artisan producers use isolated organic acids almost like a painter's palette to dial in their sourness. Citric acid gives you that bright, immediate sharpness. Malic acid offers a smooth, almost green apple-like pucker, while tartaric acid leaves a dry, tannic finish. And then there's phosphoric acid, the absolute go-to for commercial colas, which provides a very distinct, flat chemical bite. By using these isolated powders, formulators can safely drop the pH to exactly where they want it and simulate citrus profiles without having to rely on pulpy organic juices, which is great because pulp actually causes soda to fizz over and degas the second you open it. But, you can actually bypass commercial chemical formulations entirely for a more pantry-style approach. Notice this natural DIY cola syrup ingredient list. By simmering botanicals and spices, things like cinnamon, nutmeg, dried lavender, and minced ginger, with lemon juice and vanilla, you can essentially recreate the massively complex flavor profile of a cola from scratch.
And by relying on maple syrup or caramelized sugars for the base, you completely avoid using those artificial cancer-causing caramel color additives found in commercial brands.
Now, if you prefer to use essential oils like lemon, lime, and orange oil to make your cola, you're going to run into a physics problem. They are hydrophobic. They just won't mix with water. You have to use a natural emulsifier, something like gum arabic, and blend it at extremely high speeds to create a stable, milky colloidal emulsion that won't just separate and float to the top of the bottle. Oh, and here's a massive pro tip from our sources. Always add a pinch of salt to your syrup. Salt is a wildly robust flavor enhancer that reduces acid harshness, brightens up those botanicals, and actually alters the surface tension of the liquid, which gives you much smaller, more velvety bubbles. Okay, so now we have our perfectly treated water and our masterfully formulated syrup. Let's head into Section 4, Pathways to Carbonation. We know what carbonation is, and we know exactly the flavors we want, but how do we actually get the bubbles into the liquid?
You basically have two main pathways here. The first is forced carbonation. This is purely physics-based. You chill your liquid down to near freezing to maximize the gas solubility, put it in a pressure vessel like a keg, and directly inject CO2 gas into it. The second pathway is biology-based, commercial yeast fermentation. Here you're using living organisms, often champagne yeast because it has a very neutral flavor profile. You carefully rehydrate the yeast so the sudden sugar exposure doesn't shock and kill them, mix them into your sweetened soda base, and let them organically produce CO2 inside a sealed bottle. There's also a wild symbiotic fermentation option using a homemade ginger bug, but all biological methods share one absolute unbreakable rule.
And that rule is this: you must backsweeten. Yeast strictly requires fermentable sugar to create CO2. It is biologically impossible to naturally carbonate a completely sugar-free liquid. So if you're trying to make a zero-sugar diet soda using yeast, you have to add a highly precise, tiny dose of priming sugar just for the yeast to eat, and then build the actual sweet flavor profile of the drink using non-fermentable substitutes like erythritol or stevia that totally bypass the yeast metabolic pathways. All right, let's see how all of this builds into our final and frankly most critical chapter, Section 5, Surviving the Bottle Bomb. We're shifting tone a bit here because things are about to get dangerous. When you bottle conditioned soda using yeast, you aren't just making a drink. You are creating a sealed biological pressure vessel. If yeast fermentation goes unchecked, the CO2 gas inside builds up exponentially. Standard glass bottles fail somewhere between 30 and 50 psi. If that pressure limit is exceeded, you get a catastrophic structural failure, a literal bottle bomb that forcefully ejects high-velocity glass shrapnel and boiling hot liquid all across the room. So the absolutely crucial point here is exact sugar measurement, because the amount of sugar dictates the final pressure. Interestingly, the material of your bottle completely changes the math. Take a look at the difference in priming sugar needed for a 5-gallon batch. Rigid glass bottles need exactly 4 ounces of sucrose, but plastic PET bottles require 6 ounces. Why the big difference? Because plastic bottles physically expand under pressure. To get the exact same level of carbonation as you would in rigid glass, you have to increase the sugar by 50% just to counteract that physical expansion. To safely stop fermentation before a bottle bomb occurs, you must execute a strict thermal pasteurization protocol on your stovetop. Step 1. Always bottle a single plastic control bottle. Squeeze it daily. When it's rock hard, you know your glass bottles are fully carbonated. Step 2. Preheat your glass bottles in a warm sink to mitigate thermal shock, which will shatter cold glass when heated. Step 3. Heat a water bath to between 170 and 180 degrees Fahrenheit, and then, and this is vital, turn off the burner and remove the pot to prevent hot spots from cracking the glass. Step 4. Submerge the bottles, cover the pot with a heavy lid to act as a blast shield, and let them sit for 10 to 15 minutes. This destroys the yeast, immediately locking in your exact carbonation and sweetness level indefinitely. Which leaves us with one final thought. We've explored Henry's Law. We've neutralized chemical disinfectants, stabilized hydrophobic emulsions, balanced organic acids, and safely harnessed biological pressure vessels. The only question left is, are you ready to transform your kitchen into a thermodynamic beverage laboratory? The science is all there, literally just waiting for you to apply it. Thanks for learning with us on this explainer, and we'll see you next time.